to take part in this webinar series on charging ahead, exploring next generation EV technologies and the future electric mobility. I'm very happy to act as the moderator for this particular webinar, and we have three presentation by Professor Srinivasa Rao Nayak, and the other presentation by Mr. Balaji, consultant TCS, and the third one is by Dr. Vignesh Kumar, Assistant Professor NIT Trichy. And after all the presentations, we'll have the question and answer session for the participants, and then we'll have a lot of things. So let me first introduce about this particular topic, where there is a charging ahead, exploring next generation EV technologies and the future of electricity. The recent days we could see a lot of EVs into the market. Most of the car manufacturers or transportation sector companies are started introducing more and more of their electric vehicles on different natures, addressing a lot of challenges in terms of charging infrastructures and the aggregators design, and then fast chargers, the other infrastructures in vehicle, outside the vehicle. So this particular webinar will be very helpful to address some of the challenges, and those challenges are leading into some of the research directions. By all these three presentations, we could see different dimensions of this charging, the new charging topology, challenges, and how the EV market is going ahead in terms of hydrogen vehicles, all those things. Let me first introduce the first presentations by Dr. B. Srinivasa Rao Nayak, Associate Professor NIT Trichy. He had he's having lot of projects on EV charging, especially wireless chargings. He's having more than 2 crore worth projects by different agencies, CSIR and then DST, on especially designing wireless chargers for different type of platforms. And hopefully his presentation will be very much useful to understand some of the recent concepts in wireless charging technology. Okay, so after the presentations, we'll have a presentation by Mr. Balaji, consultant TCS, and the presentation by Vignesh Kumar. We'll see the presentation one by one. And now I would like to invite Dr. Srinivasa Rao Nayak for his presentations. Thank you.
So PPT is visible?
Yes, sir.
Yes, visible.
Thank you, Shankar sir, for a brief introduction. Hi, everyone. Thank you so much for having me here today. Very really excited to talk to you. Before I begin topic, first I will thanks to Kumareshan sir and Shankar sir and IEI to given me this opportunity to deliver lecture. Thank you all. I will start the topic. So I'm going to focus to explain how this wireless charging infrastructure will be work. So these are the content. This content I will go to covered about of introduction and why electric vehicle and what is the charging infrastructure will be there, plug-in charging and wireless charging and the drawbacks of plug-in charging and how the black diagram of the wireless charging and the basic principle of wireless charging and the limitation of wireless charging and the design factors. So how we can improve the wireless charging system efficiency and how to design the coils and how will we overcome that misalignment tolerance and all these things and new trends in wireless charging, and I will conclude the topic. So that the electric vehicle mission statement, so to save the environment and reduce our dependence on foreign oil, So you want to convert a gasoline powered car into an electric vehicle. So this is actually that statement. So we know go green vehicles is the global trend in the automobile industry. However, it has some limitation. So what are that means? Why you are going EV means to produce zero emission and maybe that cost. And what are the conventional vehicle causing more pollution, and you are importing fossil fuels from the importing more, so that is the cost will be more. So that's why we are going to focus, and you have to reduce global warming, and also it will be cause more pollution, right? So that's why we are going to changing this go green vehicles, so that is electric vehicle. So, however, this Go Green electric vehicle also have some limitations. There's a limited range, and the charging time will be more and more expensive. And that thus we have to overcome particularly the charging time, right? The charging infrastructure. So we have to because when you will charge that electric vehicle, so it will be take more time. And there are the two type of charging technology it will be there. So one it will be plugging charging, another one is the wireless charging. So the plugging charging, again we have some limitations. So means that tripping hazards, so that tripping hazards and other kind of maybe it's required separate space for the charging poles, and limited cable length, because and sometimes you will forget to connect the cable, charge that vehicle. So there are some drawbacks we have when it will be using plugging charging. So, and this wireless charging. So wireless charging have different types of wireless chargings. It will be there. That capacitive wireless power transfer system, and magnetic gate power transfer system, and inductive power transfer system, resonant inductive power transfer system. Different type will be there, but we have some more advantage of charging wireless charging system. It will be more safety, and automatically can charge, and more convenient. And so this we have a lot of advantage when it will be go for the wireless charging. So there again we have the static charging. So just we are while parking the vehicle we can charge it, and also while moving also. So while moving also we can charge the vehicle by using the wireless, and also we can transfer the power from bidirectional to means that vehicle to grid and grid to vehicle. So that the possibility also will be there when it will be charge these wireless charging systems. So these are the and however this already told, this is a drawback of plugging charging system. So there is a safety hazards will be there, and tripping hazards, and limited mobility, and wear tear on cables. So thus we can see the image is clearly came. Sometimes you'll forget to charge it. So this is the drawback of charging, and to overcome this all these things, so we have to go for the wireless charging. So the black diagram of wireless charging, it is the wireless charging is work similar like a transformer and induction motor. So we know that how the transformer and induction motor will be work. So that based on the induction principle, there is a stator winding is there and rotor winding it is there. So the gap between this rotor and stator winding, it will be point less than 1 mm gap. So that's why the easily we can transfer that what are the flex from the stator to the rotor winding, so that efficiency of the transformer and induction motor will be more. But here, when will we go for the wireless charging for electric vehicle? So the gap, the ground clearance, it vary vehicle to vehicle. So like the ground clearance for the light duty vehicles maybe less 150 mm to 200 mm, and if you go for the heavy duty vehicles, it will be very more than 200 mm. So it will be huge, little gap will be there. So there, due to this, that the magnetic field losses, so the efficiency will be a little efficiency of the system will be affected. So we have to improve for that. So for that we have to how it will be work this wireless charging system means. So we are supplying the grid power to the compensation network. So through this AC/DC converter, so whatever the AC grid power, we are rectifying it, and that will be supplied to the inverter. So here the inverter will be work with the high frequency, and it will be meeting to 85 kilohertz, and it will be supplied to the transmitter coil through compensation network, and whatever done, it will be produce the magnetic field. The transmitter coil produce the magnetic field, and which is linked to the receiver coil, and it will be again the received high frequency
இதுக்கப்புறம் அவங்க
AC
வந்து
voltage,
சென்டர் டீட்டெயில் அனுப்புவாங்க தெரியல.
and it will be rectified through DC-DC converter,
இதுல வந்து இந்த டீட்டெயில்
and we charge the battery. So this the working of the wireless charging system, it will be for the EV charging, wireless charging system. So the basic principle, like we are like similarly induction principle. So like a single phase AC source, 50 hertz supply with the high frequency, and which is at supplied at 85 kilohertz frequency, and which is supplied to the transmitter coil, and transmitter coil will be produce the magnetic field, and which is linked to the receiver coil. The receiver coil will be rectified that what are the received AC voltage, and it will be charge the battery. So this how this wireless charging system will be work for the static condition and dynamic conditions. So you can see the image that clearly that the transmitter coil and the receiver coil. So how it will be placed. So transmitter coil you can placing on the ground, and receiver coil will place on the bottom of the vehicle. So the ground clearance, it will be vary again vehicle to vehicle. So here based on that we have to go to design the transmitter coil and the coupled coil, and we have to improve, and we have to transmit the high power from the transmitter coil to receiver coil. So there we have a lot of benefit of when will we go for this wireless charging system. So it will be completely automatic, and we can charging station not required, and a small battery unit, because so one charge you have to designing any vehicle per charge. So suppose 100 kilometer per charge and 1000 kilometer per charge. It means when it will be 100 kilometer, 200 kilometer, and 1000 kilometer. So the battery number, so the battery size in the vehicle will be increased. So due to that, it will be further it lead the vehicle weight. So that's we have to avoid. We have to minimize the battery size. So we can go for the wireless charging. So because the charging infrastructure and also the plugging charging, again it will be take more time to charge. So you have to halt for the charging when you go for the plugging charging. So that's we have the more advantage. So when you will go for the wireless charging, so we can reduce the battery size. So when it will be reduce the battery size, so the cost of the vehicle also automatically can reduce, and throughout the journey. So like from the starting point to the destination point, when will we take the vehicle on road, so we can get the charge while moving. So that's we have the advantage. So we can go for very long range, long drive. So that we have the completely automatic. Once the charge battery will be full, so it will be cut the power in transmitter side. So while designing controller to send the signal to the transmitter side. So that's we can save the power also when it will be and battery will be full, and when it is don't want to charge the vehicle. So that's we have completely make the this wireless charging system will be automatically. So that's we have the advantage. However, we have it some limitations. That is a challenge we have to improve, and we have to focus, and we have to design. So further we have to improve this wireless charging system, either dynamic case or either static case. So that's major we have to minimize the losses. So because here we have more losses, field losses, magnetic field losses will be there. So due to that, power transfer capability will be reduced, and the overall system efficiency will be decreased. So thus we have to focus the designing of the power converters and advanced control system, and also it will be coil designs, the coupled coil designing, and also we have to take care more alignment of the coils. So then the power, the coupling will be increased, and flex linking will be increased, and power transfer will be increased, and efficiency will be increased. So thus we and also the installation cost will be little more expensive. This infrastructure. So particularly wireless charging infrastructure. So thus we have to focus. This is a challenge to us to improve this and wireless charging system and static case and dynamic. So while coming to the design, so we have to focus the coupled coil system. So this is very important to designing. So here some given shown some different structure of the coils. So we can design for the coupled coil system for static and dynamic case. So here we can give a circular coil. So it will be wound these coils in a spiral manner with the different turns. But however, we have to some limitation it is there while designing diameter. So we can't go beyond whatever the diameter. So because that based on that the center space availability of the bottom of the vehicle. So we have to consider that one, and we have to design. So this shape of the and particular dimension of the coupled coils. So and also we have the rectangular shape. So we can also go the rectangular shape. We can design it, and again they look like DD shapes. So that is again is two rectangular kind of, you can think it. So there is a like and DDQ shapes. So different structures and hexagonal square and quadruple squares and tripolar shapes. So this we have to design the coils, and we have to test the coupling system for to higher power transfer from transmitter to receiver to enhancing the system efficiency. So we to focus to design different structures for improving the power transfer system. So for we can go up to 50 kilowatt power designing also, and level 1, level 2 chargers like wireless charger. So based on that power level and this coil system, and we can improve, and we can design fast charging through wireless also. So like mostly now present the literature and researchers is focused to only level 1 chargers and level 2 chargers. So not fast chargers. So these are the coupled coils you have to go to design for how will be wireless transfer system. And another area we have to focus the compensation, because that entire what are the transmitter coil and receiver coil inductance. So we have to make the system to be in a resonance operation. So for enhancing power transfer. So we have to compensate that transmitter coil and receiver coil by using capacitor or other different kind of compensation topologies are there. So there we can use series topology, series parallel topology, parallel series topology, parallel topology. So or other LCC, LCL. So for making the entire this coupling system into resonance nature. So the power transfer will be maximum, and the efficiency will be more. So thus we have to compensate. So by this L component of the transmitter and L component of the receiver by capacitor or other topologies. So for enhancing the maximum efficiency of the coupled coil system. So there we have different types, and we can connect in the transmitter side and receiver side, and we can make it completely resonance nature, and at maybe at operating resonance operating frequency. So that we have to focus. So other important we have to for wireless charging system, either to static and dynamics, the misalignment tolerance. So we can see here given perfect alignment, when it will be a transmitter, red one is a transmitter coil, blue color coil will be the receiver coil. So when it will be both will be aligned is perfectly. So then the maximum flux linking it will be occur and coupling will be increase and mutual inductance will be more and power transfer will be occur more and efficiency will be more. So we have to always align like then the mutual inductance will be more and coupling will be more. So when it is that coil is move away from the transmitter coil, like horizontally or angularly or vertically, so then it will be misaligned will be occur. So then we have to design the coils at what tolerance this misalignment it will be get more coupling and increase the power transfer capability. So we have to design this at what tolerance is the coupling will be lost. So at what distance from away the moving coil will be moved, means receiving coil will be moved away from the transmitter coil. So we have to design and we have to do some analysis when it is the coil receiver coil will move away from the transmitter coil, at what tolerance will be coupling it will be there, and the mutual inductance will be between the coils and for enhancing the power transfer. So there we have to focus the misalignment tolerance and we for and all kind of structures. So either be circular, rectangular, DDQ, or either square, or either tripolar coils. So for all these coupled coils system, we have to design and do analysis the coupling of between these two coils with the misalignment conditions. So you can see here. So between the two coils means the air gap between the transmitter coil and the receiver coil. So when it will be very closer, means the less distance between this, the mutual inductance will be more. So the efficiency and the power transfer will be more. So when it has distance will be increased, so that again the coupling will be less. So we have to design it where the coupling loss will be there. So accordingly, we have to increase the diameter and design the coils according to per enhancing and improving the efficiency. So this we have to focus well will be when it will be misalignment tolerance will be there. So when it is the vehicle means that receiver coil will be moved away from the transmitter coil, right? So then again we have to see that how the coupling it will be, how the flux distribution between using ANSYS Maxwell or any FEM modeling, and we can do before implementing and hardware and testing of this one. So here it is they have to focus more to when it will be misalignment tolerance, these all these things. Similarly, it's given here when it is the angular misalignment occurs. So maybe is the road when it will be road will be damaged or surface will be damaged. So while parking place or either while when the vehicle is moving in the road. So due to this alignment will occur generally. So when it will be this angular misalignment occurs. So then again we have to check, you have to test and how it will be the coupling system it will be there, and how you can design this coils diameter and number of turns for improving coupling system or for improving high efficiency and maximum power transfer from the transmitter coil to receiver coil. So this we have to test before go to maybe in simulation and before go to implement that system. So here again angular and with when it will be occur the planar. So it is angular alignment it is there, and also it is the receiver coil will move away from the transmitter coil. So at the time how it will be again. So this all we have to useful for the understanding how the coupling system for the wireless power transfer system for at misalignment conditions. So now this is the current trend actually for using different advanced power converters and again the dynamic case and the different coupled coil structures, designing the different coupled coil structures, and also we have to when it will be when it in dynamic case. So in when is while vehicle is moving in moving condition. So how at what rate power will be at what rate will be charging the battery. So, right. So that we have to at a different speed again. So 20 km/h speed on this dynamic wireless charging path, or either 40 km/h speed. And when it is we are taking the vehicle with a different speed on wireless charging path in dynamic case. So we have to observe how that power transfer capabilities and what rate it will be charging that vehicle and battery. So that we have to focus and more, and while designing with the different structures, or either we can add with some magnetic bars for enhancing the magnetic field to link more to the receiver coil and increasing that power transfer and these things. So we have to do with the new to with a different speed when it is the vehicle will be taking on a wireless path. So how it will be, at what rate it will be charging the vehicle. So we have to completely new trend in we want to focus and more in toward to the research for development and when static dynamic case. So with this, I can conclude this wireless charging system. Like you have to focus when it will be coil designing. So we have to major target should we have to improve the efficiency. So while designing the coupled coil system. So when it is a static case and a dynamic case. So when it is a static, so we have to develop different structure, and which structure it will be giving better coupling system. Means that coupling will be more, and we have to design for the wireless charging system. When it will be again dynamic case, so we have to develop the coupled coils, and also you have to check that what rate it will be charging when it will be moving. So that we have to focus, and we have to improve the system efficiency, and while designing static wireless charging and dynamic wireless charging. And also this wireless charging work based on the induction principle. So that resonant inductive principle, and that is will be work, and it will be have some more advantage when it will go for wireless system. It will be more safety and more convenient, and completely you can operate it automatically. So that we have there, and also the environmental impact, because so there is no separate charging slot or space. I mean separate pole space is not required. So while the road infrastructure itself, we can install this either dynamic and this one. But when it is compared to parking place, we can install this kind of charging static wireless charging system. So no need separate like charging pole space. We can avoid that. You can charging pole. So a lot of advantage. So it will be go for this ecosystem, and also we can reduce so that battery cost when it will be this kind of provision will be there when it will be on throughout the road, right? So we can no need to halt that for the particular charging plugging means we are to halt right for plugging charging. So we can avoid that. So we can take the vehicle so throughout the means to the destination. So no need to halt it. And battery size in the vehicle, and it will be because battery will be the one of the highest cost in the electric vehicle. So to do that, it is more expensive. So we can avoid, we can minimize the vehicle cost, and that is we have more advantage when will we go for the this wireless charging system. Thank you. With this, I can conclude it, and I can stop, and thank you for everyone.
Yeah, thank you, Professor Nayak. Thanks for your presentation. I'll invite the second presentation by Mr. Balaji, TCS. Mr. Balaji, let me introduce Mr. Balaji. He has 14 plus years of experience in the field of electric and hybrid electric vehicle design, and he's working in TCS in the various projects. And he has multiple field experience like designing VCUs and EVCUs, and he's also expert in hardware in the loop and model in the loop testing and designing and different E architecture. um, he also have extensive experience and manager role in EV powertrain components and sizing of different components. um, he earned his master degree from IIT Madras and bachelor from Tyagarajar College of Engineering, Madurai. So, with this introduction, I'll just invite Mr. Balaji to give his presentation to the participants. Thank you.
Yeah, good morning, all. Am I audible?
Yes, you're audible.
Okay. Thank you, Shankar sir, for your nice introduction. And thanks, Srinivas sir, also for your previous presentation. It's good. Let me share my screen so that I could start. One second. Just give me a minute. I'm going to share this. Is my screen is visible? Hello, is my screen visible?
No.
Okay, 1 second. Oh, yeah.
Your PPT, your screen is visible, but PPT is not.
Okay, got it. Okay. So, good afternoon, everyone. Thanks for this opportunity. So basically, Srinivas sir has explained about wireless charging in detail. So now, since I have spent near about more than a decade in the industry, I see the past few years, like 3, 4 years, the trends are really changing. The day we worked around 2010s, the EVs is not in a similar lines where there are a lot of things, a lot of multitudes from different directions, or basically from different domains has changed, be it commercial. And when I say commercial, it's economical point of view, or is it a scalability point of view? There's a lot of things changed. Happy that witnessed through it. We will see what's the current trends when we say autonomous electric vehicles. We'll see why does that this particular trends, technology trends. When I say technology trends, it's a combination of multiple domains which get into in a new era. So we would see why these autonomous vehicles are getting momentum right now, and we'll also see more in detail about the vehicle to X. They call it as vehicle to everything technology. We'll have a slider on that, and after that, one of the interesting topic that is on the charging protocol or EVs. So let's start. The first thing to give a background on before we go to autonomous ones. So the past decade actually had a lot of things changing in EV industry. We used to have 2011-12. We used to have very smaller battery packs which could cover 80 kilometers to 100 kilometers max, costing like 4 or 5 times of the cost, let's say 40 to 50 lakhs. Now things have changed a lot. It attributes to the basically on the battery cost, and it further reduces the vehicle cost. So those are the things we also see a strong trend in the advanced features, be it ADAS, be it electronic things in terms of infotainment, or be it smart features. That's trend is increasing. These are the reasons where things are moving towards electric vehicle. We can ask why not ICE vehicles? When I say ICE, combustion vehicles, combustion do have that. We will see why it's moving towards autonomous electric vehicles. It's not autonomous, no, like combustion vehicles. We will see that in detail. And if we see the market trends, I think it is very interesting to see. I'm a strong believer of trends in technology happens only if it is economically feasible. People buy cars only if it is more
Can I
economically
request the
feasible.
other participants to mute? Sorry, Balaji, there is a small interruption from somewhere. I could see Mr. Sudeep Chakrabarti, Deputy Director. Can you just mute your mic? I think your mic is on. That is interrupting. Okay, Balaji, go ahead because I could still see there is a mic.
So going ahead, thank you, sir. So going ahead, what we see is basically, I'm a strong believer of the technology trends happens only when you see an economic viability. Government can support it, but at the end of the day, it has to be economically viable. That's where things are moving towards. We already have seen a one exponential curve, if I were to say, in terms of the EV penetration. We see a exponential curve already over here. And the second one is got to happen probably like 2 years from down the line, even though there is saturated market in EV right now. We wait for the second exponent. Probably that's only through autonomous or low cost EVs, the next gen EVs. That's something the teams are working on. Even the teams, European teams are working with. And this is something we all know that battery cost is falling down to a level like 115. That's if I say this, the battery cost would have been 115 like 10 years before. They would call me crazy. So it's things are changing. So that's something interesting. So this is the preamble why the and more importantly, the vehicle cost comes down because you have a battery cost coming down. Why this preamble? Because the preamble is helps us to understand why the EV exists today, and then why it has to be a thing that's evolving around. And before we go to autonomous, I want to introduce one more slide, one more picture. Basically, this helps you understand why people say about autonomous very good. You see the blue ones. Blue ones are the revenues the company make. The red ones are the valuation. Valuation means that what company values at how much I'm willing to buy that company for. You see a difference just in Tesla. Tesla is the first one who introduced autonomous in it. So if you see, basically the revenues like peanuts with respect to Volkswagen and Toyota, they are the top brands in terms of number of cars sold. They are like very high revenue in terms of like 160x. The reason being, they are not actually a automotive company. They are a software company, to be frank. They built the first autonomous systems. So the valuation happens only through the technological innovation. So they see a potential in the technology. So that's where the market grows in. Basically, your market cap goes in. So having said this, let's jump into the autonomous. I think let's get into technical. So that's like Tesla I said, it's not an auto company. That's where people are moving towards autonomous. The reason being, so this is a change in era, I would say. Reason being, so you don't need a driver, and it has an operational cost benefit and also in terms of safety benefits. So first of all, what is autonomous? Basically, as we all know, like it has sensors in place, be it radar or cameras. Sensors in place. You have an AI. Basically, when I say AI, it's a machine learning thing. It's not like ChatGPT that what you see. It's not a generative AI, but it's an AI based on a deep learning technology. It's one part of an AI basically. So it has a machine learning algorithms which has a learning based on the existing data already available. Basically, when I say existing data, we already driven the vehicle with multiple places, lots of tons and tons of data. With that, the machine learning algorithm is trained to act decisively. Basically, the more you drive, you learn better, right? So the same way. So basically, to avoid human intervention, it should do it without any human intervention. That's the ultimate goal. When we say that, we are not there at for full autonomous vehicles today. We don't have fully autonomous vehicles as we speak, even though multiple OE claims. So that's where the definition of how the autonomy has to be defined comes in. So then Tesla says I'm already a level 5, but it's not true that we know. Then how do we say somebody has achieved a full automation? That's where SAE has defined 6 levels, basically 5 levels, with level 0 as a no driving automation. So there is a definition in the industry which tells, based on what you could do with the car, what automation the car could do, the levels are being defined. Let's say level 0 is something like no automation, no support from the vehicle. Basically, it'll have ABS, it'll have EBS, it'll have a stability program, and everything else will do. But braking, acceleration, steering, everything is done by user. If you go and hit the car, it'll hit. So it is all just intention by the driver. So if you just go behind in a car and then accelerate, it'll hit for sure. So it doesn't have any automatic braking, for instance. It doesn't do any action on its own. It doesn't do any cognition on its own. It'll have safety features like ABS, EBS, and all that stability programs would be there. But it is called as a no driving automation because it doesn't do anything on its own intentionally. So when you press brake only, the ABS would activate. So otherwise it never activates. So there is no cognitive action from the vehicle side that is called as no driving automation. So there are different levels on which it is there. People go to the next slide and see. Um, so as we say, like it has a basic safety issues which are already available in level 0. If you come to level 1, basically the driver assistance, it's basically the driver assistance is to help the driver to avoid, let's say, his mistakes or mistakes from other car. So, for instance, it can be a lane keep assist. For example, we drive in a in a in a in a turning, we don't keep the lane. The car will correct on its own, or it can be like adaptive cruise control. For instance, if we drive along highway, so we could do an adaptive cruise where we could set a speed and then drive car takes care of its own cruise. Basically it maintains its speed. When we say adaptive, it's called as cruise control. That people say adaptive because it adapts to the situation. Let's say if it is a downhill, it's uphill, it takes care of the speed. If there is a vehicle before it brakes on its own. So that's why it's called adaptive. It's adaptive to the environment or the situation that's given. So these are all called as features which helps the driver, but still he owns the responsibility of the driver. So it is called as a level 1. It just assists the driver. It just helps the driver to avoid his fatigue. That's the idea of driver assistance. In today, like most of the developed markets, we cannot see a car with level 0, but we do see in India. But most of the developed markets don't have level 0 cars. They one form or the other, LK or ACC or some form or the other, driver assistance is present in even in the basic model. We would say so. It's not very far, like even in India and in the developing markets, the level 1 is going to be a standard. Like we have 6 airbags as a standard in most models today. Similarly, the driver assistance is going to be like going to be a standard in Indian market coming not in a decade, like 4 5 years from now. So there comes a level where it driver assistance is basically to avoid a driver fatigue. The level 2 basically takes care of some level of controlling, like basically it can control the lateral and longitudinal. I did not mention this. Basically, when we say lateral, it's on LK, lane keep assist, or longitudinal. Basically, it can be a cruise control or it can be adaptive cruise. So this is longitudinal. Yeah. The driver assistance normally does level 1 normally do any one of them. It can do a ACC or it can do a LKA. But in case of partial driving automation, it do both, like longitudinal and lateral dynamics. Both are being handled. So here you will have additional sensors that we would see later in the next slides. But here it takes care of its own control. For instance, some of the examples today in India markets are XUV700. Like you have Tata Curve. There are like good cars coming up with level 2 automation already in India, where it can take care of itself. It can drive on its own with LK and ACC in place. You have to set cruise and then you have to ensure LK is automatically activated. So once that is done, driver can just sit. Basically, he should actually take a control whenever needed. So the idea here is the driver is still responsible at level 2. He should continuously monitor what vehicle is doing. He should take control whenever needed, because the software and basically this car doesn't own any responsibility at this level 2 also. So basically it helps driver to take off his pedals and steering wheel for a quite often, so he don't have to hold the steering wheel technically, and he can lift off his leg from the pedals. The car could keep driving. That's possible. But legislatively he has to keep the hands on the steering wheel, by the way, but he has to take control of the vehicle on his own way. So this is called as a level 2. It's mostly available in some of the top ends in India. It's mostly in developed countries. There are many models on this. And conditional automation is something like driver could do something like basically non-driving activities where the vehicle will take care of its own in terms of the driving actually. So if you just set this location, it drives automatically on its own, but still the responsibility still lies with the user. Driver takes the full responsibility, but he can get away from driving for extended period of time. It's level 2 and level 3 basically. It's a maturity improvement. Yeah, there is a lot goes in behind, like in terms of sensors or in terms of the algorithms that we built in, but it's more on the maturity front, where they occasionally can engage in non-driving. He don't have to hold the steering wheel. He can just do something, but he still have to keep an eye on what the vehicle is doing. So this is level 3 is something that people already have achieved in some form or the other. People call it 2 plus, not 3. Sometimes people call it 2 plus because some of them are not achievable at level 3. So they call it as 2 plus. There are very few models which achieve level 3 already. So probably the Benz is the first one who got this. And going to level 4. Level 4 is where something driver could completely, it's a highway driving automation, if I were to say. If you, for a given condition, under certain conditions, driver don't have to look at the vehicle. So it is not everywhere. It's at certain conditions. Let's say you've given a defined route, or there are routes given for this autonomous vehicle. So there you could drive. They are still evolving. When I say highway drives, they are still evolving. How do we allow particular highway for this? There are still protocols and government regulations coming into this. Um, there are many, and similarly, parking garage. For example, you leave Tesla models and then say go to parking. It'll go on its own even. So these all comes under level 4. But the problem is this particular one cannot be, let's say, the autonomous cannot be achieved at every place, for instance. So that's a problem. It is only defined for a limited places and a controlled environments. When I say controlled environments, it's outside world, but still it's on a limited places. That's what called as level 4 automation. Even though Tesla claims it's to be level 4, but it's still in level 3. So it's people are trying to get into level 4 right now. The level 5 is something people are demonstrating, and there are few protos being pushed out, be it Google autonomous car, or it's Apple car, or it's a Waymo. So like there are many people build protos for level 5. The level 5 doesn't have any steering wheel, no pedals, nothing. You just sit inside the car, it'll drive on its own. You just have to tell in your app where you want to go, that's it. And it takes care of on its own. So you cannot even control because you don't have any control system. So it is fully autonomous one. So there are legal complications that's running around. So people are looking into how do we, even though they have softwares, but the corner cases can never be proven because they need billions and billions of kilometers of data to even to prove it's safe, and so it's very complicated to get a regulatory certification and also the clearing the frameworks. That's something currently going on, but there are people who like nearly achieve this, but at the proto levels, I would say, not at the production levels. Yeah. So this is the overall idea where the how the automation levels translate into your autonomous vehicles. So coming down, what is really it contains? That's something that's interesting to see. We have seen what it could do, but how it is doing is what given over here. So typically, like autonomous systems, the cars that we work with, basically it's split into three different type of sensors, but there are nuances into subdivisions and so on. But fundamentally, at a top level, you could build into three bins. One is camera based. Basically, it's a typical camera, but it's a auto grade and high resolution cameras. And be it lidar, it's a light based radar basically. And radar we already have it from, be it used inside water or so. The radar and lidar is an advanced version of radar. So these are three buckets mainly they've put it into, even though we have ultrasound, but mostly these three are the ones people to use. So in terms of each one has its own benefits and disadvantages. So normally OEs would, when I say OE, like original equipment manufacturers, auto companies, they use one or two combination to offset its one disadvantage. For example, camera is bad at something, we do have radar in place, and then some people use lidar and radar together for improving the modeling accuracy. Some people use only cameras. For instance, Tesla use only cameras. They did not use lidar or radar. They use a camera and ultrasound in place. So it depends on OE strategy, how they want, how their algorithm is basically, because it's not just with only sensors. Sensors are fundamental core in getting the data, but it also depends on how like how their learning algorithm is already. It is also based on how much training data they already have, how much kilometers they have already covered. So there are multiple things. But at the top level, we could put it in three bins. So come to camera, it's a sensory. We all know, like it takes images, so it helps in modeling very good. When you say modeling, how the shape of the system would be, if you have multitude of cameras instead of one camera, you have a depth camera in place. You can have a 3D information. You can have like a physical representation of, is it a car, is it of this shape, or is it a cycle, is it a bike. It can be easily identified with cameras, but only problem with camera is it really bad at poor weather. It's very once it is foggy, it is very difficult to differentiate things out, like our eyes basically. So it comes with our own eyes problems, I would say. So but interestingly, Tesla, as I said, so their sensor fusion is in such a way with ultrasound and camera. They are able to do it with camera only because they have a very reinforced model where they have tons of data of. They are driving this from 2014, the autonomous semi-autonomous system. They call it as autopilot. They do it. They have billions of kilometers of data, so they're able to do it with camera. That's why I say it's not just about the sensor, it's also about the what our model is. Model is nothing but basically how we think when we drive. So if we are experienced driver, we could drive off difficult situations. So that's a idea. So in terms of lidar, let's see what's radar. Radar is it's unaffected by weather condition because it's not an like image visionary vision sensory. So it's easy because it's a radar signal, it's sent out, and it try to understand the shape, and if there is a blockage, what this blockage is, it a cycle, is it a car. It's very easy, it doesn't bother about weather conditions. That's why it is typically used for emergency braking, because we know there is something is there, but we may not know clearly what it is. That's why its definition modeling is very difficult. Like between cycle and motorcycle, or between a car and a smaller trucks, very difficult to distinguish between two similar items. But it knows something is there, so it is typically used for emergency braking. So whether it is cycle or motorcycle doesn't matter. You have to brake. So that's the reason they typically use this for emergency braking. The weighing factor for radar is higher for this emergency braking. So when they take a decision to brake, they get data from lidar and radar together, or radar and camera together. So if camera says nobody is there, if radar says somebody is there, radar takes a precedence. So radar says somebody is there, just break it. So don't worry about what camera says. So that's why it takes a precedence. So it's a default sensor for emergency braking when we typically use. But it is very low definition modeling tells us it doesn't know what it is. So in some of the cases, not most cases. Most cases it could find, but in some cases it's very difficult to find what that car is. It a car? Is it a small truck? It's very difficult to find. That's a disadvantage with radar. But in case of a lidar, it's kind of an advanced version of radar. Since it comes with the like base rate detection. It's good in 3D modeling because it gets both the benefits of camera and radar together, and it gets the benefits of not affected by weather from radar, so it doesn't have imagery perception, so it's not affected by weather also. But only problem is it's still used by limited things, and then it is sophisticated and cost wise is also higher. That's something people are working on and getting this lidar into. But some people still prefer cameras only, like Tesla. That's depends on their strategy. If you see this particular image, this ultrasound is something that Tesla used for this adaptive cruise and emergency braking. So it's enough to ensure the safety. So they don't have to rely on radar like here, like we said, default sensor for emergency braking. But in terms of the way it is positioned, you could see here, like the ultrasound is something this far off, and lidar and let's say the long range radars are all for basically for cross alert and blind spot detection, and camera is basically for 360 to sense what's there. And how do we fusion and get the sense out of it? That relies on the machine learning algorithm they had in their main in the central computer. So for a different purpose, different sensors used. So that's the way it is. I think we don't have questions, so I think we cannot ask questions, so we will move on. So yeah, as I said, like there are multiple sensors used to fusion. Basically, when you say fusion, you take a decision out from multiple inputs. You take multiple inputs from one from camera, one from radar, and one from, let's say, camera and radar, for instance. Let's say we take these two inputs, and what do we decide when camera says no, when nobody is there in front of you, and then radar says somebody is there in front of you? Who takes a decision? So it depends on who is good at what. So that's why people typically use multiple buckets, cameras and radars, or sometimes cameras and lidar together, but not radar and lidar together, but cameras and lidar together. And they do a fusion, basically take a decision, weighing the decision based on who's good at what, and then come up with a final solution. So that is called as a Spencer fusion. Spencer fusion is multiple inputs taken into, and then decide something. So here, if you see, like in terms of camera, the long tunnel position is very bad. If you cannot sense this left side car, but lateral position is accurate when you see. So similarly, radar has its own advantage, lidar. So when you fusion both of them together, so let's say if you fusion this camera and radar together, just get into like you get all of them accurate. Let's say longitudinal or lateral or velocity positions. So it depends on what we want to use. So in case of this, for instance, Tesla basically uses ultrasound. So we have a lateral position available, this car available, but this car not available. So don't go for radar, go for an ultrasound. That's possible. So it depends. The ultrasound is not mentioned here, but it depends on whose strategy, how they want to do it. But at the end of the day, sensor fusion tells us the best of every worlds, like best of camera, best of radar, and best of lidar. And going down, let me go to the next slide. Okay, we have seen autonomous electric vehicles, and most of the OEs work on autonomous electric vehicles. I'm sure some of you have. Why not autonomous? I say ICE here because it's internal word, but internal combustion engines. It's a conventional vehicles. So why not autonomous conventional vehicles? Why not engine with an autonomous vehicle? Why we don't have? So there are
Mr.
vehicles
Balaji,
which
sorry to interrupt. How long you takes more time?
maybe 10 more minutes.
Hello.
How long do I have?
How long? Yeah, 20
Maybe
minutes
10 more
only is
minutes.
for each presentation.
Okay, sorry.
Then maybe 5 minutes. 5 minutes.
Sure,
Just
sure.
one more
I'll go into.
presentation is question answer session. Will take 2 minutes.
Sure. Thank you. So one of the fundamental reasons why we go for autonomous electric vehicles, not ICE, is basically EVs are simpler in electronic architecture, be it a central zone computers, and more importantly, EVs are based on software-centric design compared to most of the ICE components are internal combustion vehicle components are mechanical, non-electronic items. So and basically simplicity in EV powertrain. That's the reason we discuss about a autonomous electric vehicles, not autonomous ICE. Coming to, I'll quickly see through this. This is how the typical ICE would look like. This is how a typical EV would look like, where there is a central computer, everybody else is connected to this. So it's easy to take a decision. Here it's very difficult because there are multiple components from multiple domains. It's very difficult to take a decision at a given point. So zonals are better, are evolving central architecture, they call it as. This is called a central architecture. So it's an evolving one. So it's very difficult to convert ICE to this. So people go for autonomous EVs. And V2X, this I think to an extent we know it. Basically, vehicle to different items. For instance, be it infrastructure in terms of communication, or be it vehicle to vehicle, communicate with other vehicle to say there's some accident happening, or there is a cornering, there is a vehicle, there's a vehicle up front, don't overtake, or be it connection to pedestrian, say that the vehicle is coming because it's an EV, doesn't have a sound, so giving an alert to a pedestrian, or giving an information in phone to user, or connect to server uh, to do the prognosis for the vehicle issues. Those all possible. There are still some question marks. There's still evolving field over here. Going down quickly to charging protocol, I think we have limited time. So this is something that I want to tell you. Like the charging is one of the place where there is a lot of complications involved, because there are multiple protocols involved and multiple countries, and everyone wants their charging type. So normally charging protocol is like how the vehicle charges, how the charger and vehicle communicates. So it communicates by different methods, PWM, PLC, or CAN. So there are multiple charging protocols with different communication. So there are a lot of confusing terminologies. If you are new to this, it's a lot of confusing terminologies. I just want to clarify that. So the terminologies are given in terms of levels, modes, and types. So probably we've shared this presentation. You can go through that. There is a levels and there is a modes and there is a types. We'll quickly see what it is. So charging based on types, when you say types, they call it based on kind of connector and kind of protocol that you're going to use. Basically, what communication protocol that you're going to use. So different countries adopt different protocols. To quickly say, whatever you see small rounds, these are all AC chargers. Whatever you see this additional, these are all called DC chargers. And CHAdeMOs comes, this small rounds you see, the CHAdeMO alone comes with DC. So whichever big rounds you see, those are all DCs. The small ones are all like ACs. Very small ones are communication pins. So the different protocols, CCS, CHAdeMO, and GPT. These are the three major protocols based on the country you live in. So yeah, all OEs have different type of charger protocols based on where do they sell. And modes, I think modes is based on how much, where do you charge basically. Mode 1 is at household, mode 2 is at household, but depends on what protection you do have, ICBCD. And mode 3 is something like it, you charge at a different, at a higher power, let's say 7 kilowatt, 3 to 7 kilowatt. You have a cable in it. Mode 4 is basically a DC charger where there is a converter sits inside here and then charges the vehicle through CCS2 or CHAdeMO. So the mode 1 to 3 is called AC charging. Mode 4 is the DC charging to put it at a higher level. And in terms of level of charging is again comes down to the type of charging what you use. Basically, this level 1 and level 2 are like low power AC chargings, and level 3 is a high voltage DC charger. So these two are AC, these two are this is one is DC. So this Majusm 1 to 3 is basically falls into level 1 and 2, and level 3 is for DC charging. People use different terms, so it's sometimes confusing. I just want to clarify. So this is another type of charging where there is a Panto. This is typically for larger battery packs like buses and and it would charge like also for some special chemistries like titanium, lithium titanates. So they have different types of charger, like inverted and non-inverted. I think you could spend more time. There's a lot of literature available. You could see. This is for ultra high power charging. This will be somewhere around 300 to like 600 kilowatt charging powers we are speaking about. And this is like same protocol, like people do use CCS for this. Only the additional complication in terms of positioning bus and all that would come in additional. And otherwise, it's a straightforward CCS communication through PLC. That's all I have. Any questions? Probably I can take it at the end if that's what the process is. Thank you. Thanks for your time.
Yeah, thanks for your nice presentation. Yeah.
Thank you. Thank you.
Now we'll go for yeah. Now we'll go for the other presentation by Dr. Vignesh Kumar, Assistant Professor, INIT Trichy. Dr. Vignesh Kumar, having more than 5 years experience in the teaching field. He was initially with NIT Surathkal as assistant professor, and he joined NIT Trichy recently. He completed PhD from National Institute of Technology Trichy itself, and he has vast experience on different converter topologies, especially for e-mobility applications. So I invite Dr. Vignesh Kumar to have his presentation to the participants.
Yeah.
Yes.
So, good evening, everyone. Thanks, Professor Sankar sir, for a warm welcome. Um, I would also like to extend my thanks to Professor Kumarasan sir and also IEI for having me this opportunity to take part in this webinar as one of the panelists, so that I can also discuss on the topic of exploring next-gen EV technologies. So my co-panelists, Dr. P. Srinivasarao Naik sir has discussed about wireless charging technologies, and Mr. Balaji from DCS has given a nice presentation on autonomous EV systems. So I'm basically a power electronics person. I work on development of power converters, and also its control techniques. So from power electronics perspective, I would like to focus today's presentation on wide bandgap devices for EV systems on the V2X EV charging systems. This is already touched by Mr. Balaji, but still I will throw some snippets onto that. Then I'll also have a discussion on sustainable EV charging systems. So I think power electronics plays a vital role in enhancing the performance of EV systems. So day by day, researchers are coming up with new topologies, and next generation power electronic devices are coming up, so which can enhance the power converters performance in topology wise and also from control perspective. So power electronics has a major role to enhance the EV performance and also to take the EV to next generation. So with that aspect, I have or I keep my presentation focused on these topics. So let us move on to wide bandgap devices. So before proceeding into that, so let us have a brief look at power electronics in EV systems. So if we take a EV system, we can classify this as power converters that are present inside my EV and which are present outside the EV. So that basically the power converters which are part of the EV, inside EV, that we call it as EV powertrain. So which basically transmits the energy from battery to the traction motor. Okay, so this we have EV battery to, and then a DC-DC converter, then DC to AC converter to power up my electric motor. So in addition to that, we do also need some other DC-DC converters, so to supply the auxiliary systems like infotainment and other sensor units. So all these requires power supply. So that is collectively called as auxiliary power supply units. So which also require a power converter stages. So in addition to that, we can have onboard chargers, which are basically a low power chargers. So that provision can also be there in the EV. So in that case, it again need to have one more power stage, which can convert the AC grid power into the DC, so that it can be tailored to the battery needs. Okay, so coming to the charging systems, we have DC fast charging stations which are at high power levels in the range of tens of kilowatts. So they also need high power converters which has basically AC/DC and DC/DC stages. So the power electronics plays a vital role in the entire EV systems, right from whether it is a charging side or it is a electric power train side. So meaning that we need to have very good efficient power conversion so as to improve the overall performance of my EV systems. So these are all the areas that should be focused. So first we should have an efficient power conversion from battery to motor, and also we should have power converters which are capable of handling this regenerative braking, which is basically the energy recovery process. And our power converter should also handle the torque control of my motor, and also it should have a speed regulation. So moreover, my power converter should also, that means the power converters that are employed in charging system should also have efficient charging process and also a fast charging process. My power devices that are used, power semiconductor devices that are used in the power converters in charging systems should be capable enough to fast act. Okay, so all these things are again the part of the requirement for power converters. And also the very important point is battery management systems, which design or which facilitates the prolonged or long-lasting operation of the battery. So this also requires some power electronic systems which facilitates the management or condition monitoring of the battery systems. So all these things added together, it should power converter should also contribute to the vehicle weight reduction. So these are all the major requirements for a power semiconductor devices to be used in the power converters, which should lead to these outcomes. So at present, most of the power electronic converters which are being used, either it is a traction inverter or it is a EV charger, they basically employ silicon devices. Now with the introduction of SiC and GaN devices, which we call collectively as wide band gap devices into the market, many of the EV providers they have started to employ SiC devices widely into their traction inverters and the charging systems, but GaN is still evolving. So let us have a look onto the material properties of silicon SiC GaN, so that we could understand the advantages of SiC and GaN compared over silicon, or what kind of device characteristics they can provide. So if you look at these are all the major critical parameters which differentiates them from the conventional silicon based devices. So first one is band gap energy. So it is almost 1.12 for silicon, and it is 3.26 for silicon carbide and 3.39 for GaN devices. So here band gap is more, means we have a strong bonding between the atoms, so which means that my electrons cannot be quickly removed from the atomic forces, or it cannot be excited to the higher energy level. So that means it can provide higher thermal stability and it can withstand high operating temperatures. And also next parameter is critical electric field. This also has almost similar range for silicon carbide and GaN devices. Then coming to the thermal conductivity, we have a very significantly high value for silicon carbide. This makes silicon carbide to be operated at higher power levels. So basically GaN devices are used for low power levels, because in the later slides we will see the commercially available GaN devices and SiC devices rating, which would give us an idea. So for which applications or which power level we have to use which devices. Then we have saturated electron drift velocity, so which is very high for silicon carbide and GaN devices. This makes them to have a very high switching speeds, so they can be turned on and off at the ranges of more than 500 kilohertz or in megahertz range. So this is the reason for that, and also they can have better operating temperatures compared to the silicon device. So this makes the wide band gap devices basically silicon carbide and GaN for a suitable candidates for the enhancement of power converter performances. So we will see the other advantages from the device properties, so that what is the overall performance output of my power converter when it is employed with wide band gap devices. So the material properties that we have seen in the previous slides have resulted in the device characteristics. So here is a comparison of important device characteristics with respect to power converter operation. So we have basically a comparison of silicon carbide and GaN devices. So you can see here the on-state resistance for GaN devices much lower compared to the silicon devices. And also the gate charge capability is very lower for GaN device compared to silicon device, then whereas silicon carbide is between these two. Then we have switch on time, which is 30 to 100 nanoseconds for silicon based devices and 20 to 30 nanoseconds for silicon carbide devices. And here is the major difference that you can see, or I could say a significantly very low turn on time, which makes the GaN devices to be operated at megahertz range. So here similarly switch off time also have the same trend as that of switch on time for these three devices. Okay, so these from these device characteristics comparison, we could understand that how WBG devices can outperform the silicon based devices when it is being employed to the power converter development. So we have here the comparison of WBG devices when it is employed for different applications, that is motor drive applications, and then onboard converters and chargers. Coming to the switching frequency level, we can have, when it comes to motor drive, up to 10 to 20 kilohertz for silicon and the WBG devices, whereas for onboard converters and chargers, we can go up to more than 500 kilohertz. Okay, and the efficiency, in terms of efficiency, WBG devices can give almost 1.4 to 4.4% increase in case of motor drive applications, whereas for onboard converter applications it can contribute 0.5 to 3.75% of efficiency improvement. And similarly for power density, this is again another major advantage with while we employ WBG devices for the power converters. So the high frequency operation, or the capability of WBG devices to be operated at high frequency, reduces my filter size and other magnetics requirements. So this gives a significant increase in the power density level that ultimately reduces the total system size, weight, and also the ultimately the cost. So you can see here While employing WBG devices for motor drive applications, it is we could get almost 200 to 300 percentage of power density level increment in the power density level. The same way we could get almost 200 to 900 percentage increase for onboard converters applications. Okay, when we employ WBG devices. So this is basically because of reduction in the size of magnetics. So my magnetic cores can be reduced when I have very less inductance requirement, and also all the other core accessories like bobbin requirement, number of coils, and also the thermal management system. So everything can be reduces, and that collectively puts the overall reduced volume to almost 76 percentage in the onboard converters applications when it is employed with WBG devices. So this is the best comparison table that is being taken from this particular reference, which will reveal the advantages of WBG devices when it is compared with silicon devices for power converters. Okay. So as we said, here we have a look of SiC devices and GaN devices and how they are commercially available in the market with what packages. So we have SiC devices of in TO247, TO252, TO247 packages, and also we have power modules with SiC devices. And if you see the rating, SiC devices can come as SiC diodes, SiC transistors, and SiC power modules, whereas we have GaN devices as GaN transistors. So SiC diodes can have the voltage rating of almost 1.7 kilowatt and current rating of almost 50 ampere, whereas SiC transistors can have 1.7 kilovolt voltage rating, current rating up to 120 ampere. And power modules, we can have intelligent power modules for SiC devices, which can handle almost 70 to 800 amperes. Okay, so these SiC devices are mainly recommended for the high power levels because of their capability to withstand high temperature and high operating temperature conditions. So the application area mostly falls on high power converters, motor drive applications, and chargers. And here we have GaN devices. They mostly comes as SMD devices. So we have here very low power rated GaN devices. Few are TO247 packages, and some other are in LSON. Some are in even QFN packages. Also, we have GaN devices. Then we can have the voltages up to 900 volt only, whereas SiC devices are available up to 1.7 kilovolt, and here GaN devices are available with voltage rating up to 900 volt. Mostly 600 volt devices are very common in the market, and the current ratings can go up to 150 ampere. So the GaN devices are mostly restricted to low power applications, and it is best suitable for onboard chargers which operate at low power compared to the offboard DC chargers. These are some of the SiC and GaN devices provided by few manufacturers. Here we can have a look at what is the power rating. Okay, and we have here for SiC power devices mostly available in diodes and transistors, and we have from Microsemi Corporations and Infineon Technologies as SiC devices as a full diode bridge module and single and three-phase three-level modules. So they have the ratings of almost single module can be rated for 1.2 to 1.7 kilowatt and 580 to 225 amperes. And GaN power devices are mainly from Transform, Nexperia, EPC, GaN systems, and their voltage levels range around 600 to 900 volt. You could see here, and the current ratings would also very less compared to SiC devices, but they can have high operating frequency. And the packaging also, it is sometimes even some of the EPC devices I have worked on has a bad die. So, and most of them comes as SMD devices. Okay, so now After having a look on to the advantages of WPG devices, let us see what are all the major challenges when we employ WPG devices for power converters. First is from the manufacturing side, when we grow the WPG devices, they have greater complexity compared to fabricating a silicon devices, because their die level is very small and also the wafer cost is more. So they have more complexity compared to silicon fabrication of silicon based devices. And coming to packaging and integration, so packaging in the sense, as we see in the last slide, this is what we mean by packaging, PQF and TQ247. Okay, so packaging and integration is also very difficult, because these devices have to withstand high voltage stress, and also they have to be operated at high frequency. So all these things adds complexity to packaging of these devices. And coming to switching losses and efficiency, of course, we know that these, when they are hot switched, definitely there is going to be the switching losses, because they operate at more than 500 kilohertz to 1 megahertz. So they have the capability to operate at that frequency. So obviously, hot switching, when we go, switching losses will be more, and so it is better to have a soft switching approach for when we employ this GAN based devices. Then we have uh, challenges with the driver circuits and control, because my driver, which is providing gate pulse to the silicon and GAN devices, should also be capable of operating at such a high speeds, and they should also avoid the loop inductances and other parasitic inductances when it comes to the PCB layouts. And my control loops also should be designed to accommodate such a fast switching times, because control loop should be fast, active enough, or it should be fast enough to uh, put the things in coordination. Then temperature sensitivity, because the GAN and SIG devices are going to have a very small, are going to be in very small size, and at the same time, if we look at the temperature that they are going to operate, it will be much greater than the silicon based devices. So they are sensitive to temperature, and better thermal management systems are required. Okay, this is another challenge. And coming to ecosystems and expertise, so industry should have expertise among the engineers, to those who can actually design the GAN based power converters to utilize it.
Dr. Vignesh, you have 5 more minutes. Huh?
Yes, sir, sure. I'll speed up. Yeah. Okay, so these are some of the trends on WPG semiconductor devices. So we have these models which have already employed SiC-based traction inverters. So we have Tesla Model 3 is the first one to employ SiC-based traction inverters in their EV powertrain, and followed by Toyota Camry hybrid model, Nissan Ariya, Kia EV6, Hyundai. So these are few examples. There are so many other model market. Yeah. Okay. So then coming to the gallium nitride vehicle, so this one was gallium nitride is still evolving technology. So this one was introduced in 2019 Tokyo Motor Show. It was a collaborative work by Nagoya University and Future Materials and Systems Research Institute, Toyota Advanced Power Electronics. So here, this is a buggy type vehicle wherein they have used GAN inverter in powertrain, and also GAN DC-DC converters for onboard chargers. They have also used GAN-based power converters for lighting units and other auxiliary power supplies. So this could result in efficiency improvement by 20% and also 75% reduction in the size of system. Okay, so this is also successfully road tested at Fuji Speedway in Japan. So this is the all GAN vehicle, so which is completely employed with GAN technology. And coming to the charging systems, these providers, they use silicon carbide based power converters in their high power charging systems. So, okay. So coming to V2X technology, I'll also quickly wrap up this. So V2X is by definition, is the use of EV batteries which are sitting idle and not being currently used for mobility purpose to provide valuable power back to everything. So this everything, it depends on the load or the point to where the EV battery is supplying power. So it can be vehicle to grid, it can be vehicle to home, vehicle to building, vehicle to load, and vehicle to vehicle. So from the hardware point, the most important thing is when we have grid to vehicle, it can be unidirectional. But when we want to have V2X, so we need to have all the power converters to be a bidirectional one. So vehicle to grid, you can see from this picture. So which means that my EV battery can act as a distributed generating resources which can contribute power to the grid. But the thing is that it requires a specific hardware, and also it needs proper regulations and accurate metering. So these are all the limitations to move forward with this technology. Then vehicle to home, it is simple like having inverter in our home in which we can use the EV battery to supply power to the home in case of emergency. So this happens behind the meter, so not before the meter. So it can be easily implemented at residential levels. Then we have vehicle to building. This is also similar to grid, but here only thing is that it does not require any additional grid infrastructure. It is constrained to a particular building, and we need to have a building energy management system so as to coordinate the vehicle charging and other things, because this will reduce the entire building energy cost. So building energy cost, we can have demand cost, fixed cost, and energy cost. So if we charge the vehicle or use the vehicle power to supply the building loads during the peak hours, then the energy cost can be reduced, and also charging can be coordinated in such a way to reduce the maximum demand of that particular building. So that's why this building energy management system is essential for implementing this vehicle to building. Vehicle to load is a very easiest form of V2X technology. So here it can have 3-pin plug or a specific type of connector. So like we have mobile charger in our conventional vehicle. So EVs can be used to supply any 220 volt loads. Then vehicle to vehicle also a kind of V2X. So this can charge up the isolated vehicles during emergency case, and also it can be connected to charging stations to share the power among the EVs. So some of the applications, as we know, vehicle to grid, when we have DG source, it can help us in leveling the load, so that we can by coordinating the charging, or by having the proper coordinated control for different operating modes, it is possible to allocate the energy so that the load curve is flat enough. And then we have so all these things I have discussed. So then coming to sustainable EV charging systems, so here to make the EV as a truly net zero emission system, we need to have renewable energy integrated to it, so that the power from renewable energy is utilized to charge the EV battery, rather than depending on the grid energy. So here it's not enough. There are challenges as existing in the conventional renewable energy integration to grid. So the same challenges will carry over here also. But in addition to that, when we introduce renewable energy systems, we should have a coordinated EV load. So as you see here, this particular pattern, this is the particular pattern of PV power output. And my EV load, if it is not coordinated, it goes on its own way. But it can be coordinated so that the big solar pattern gets matched with the EV charging pattern. This is a topology for renewable integrated EV charging system. So here we have a PV array, which is all the renewable energy systems are connected to DC bus. So this which forms a DC microgrid, and you can have PV to DC-DC converter which performs the MPPT control. When it comes to wind, we need to have again AC to DC and DC to DC. That makes the DC bus.
Vignesh, shall we wind up, because question and answer session also there?
Yeah, yes, sir. Last slide.
Most of-
Only one more slide.
Okay.
So the same way we can have a integration of renewable energy to the AC bus also. So this is a topology depicting that. And yeah, I conclude here. Thank you, sir, for the thank you for all the attendees for the patient to listen to this. Thank you, everyone. Thank you.
Thank you, Vignesh. Thank you, because we are running out of time. That's why I'm about to rush it, because
Yeah, yes, sir. Yes, sir. Yeah, I can understand.
Yeah. Thank you. Yeah. Now we'll move to the question and answer sessions. We'll briefly go for a few questions asked by the participants. I'll read some of the relevant questions. I may not be able to read all the questions raised by the participants. So the first of all, thanks to all the speakers for presenting wonderful topics on the various heads. Hopefully, the participants would have gained a lot by hearing your lectures. Let me read the questions one by one. I'll 1 minute. Yeah. So this is a question by Yash Arora. He's asking about, sir, how much probability we can depend fully on EV than fuel-based vehicles? Maybe can you request Mr. Balaji to answer this? Hello? Hello, Mr. Balaji, are you available? Professor Nayak?
Yes, sir.
What is the question, sir? Can you come again once?
Yeah. I'll see the Yash Arora. This question is asked by Yash Arora, that how much probability we can depend fully on EV and fuel-based vehicles?
Yeah, the probability depends on the EV charging infrastructure. Basically, see, being a consumer or a EV buyer, so what I would like, I want my EV to be charged quickly. So I want my EV to be behave in a manner as that of my conventional vehicle. Okay, so it all depends upon the charging infrastructure, and nowadays we have the charging points being installed almost in all shopping complexes, malls, pump stations, and you can advanced EVs are having even GPS systems to display where the charging infrastructures, charging points are available. So the usage of EV or moving to probability of moving towards EV depends on these developments. Yeah.
Yeah. Thank you, Vignesh. The next question is by Amrish Kumar. This may be relevant to Professor Nayak. He's asking about designing wireless infrastructure on road will be cost effective or not, or it is effective to have this type of charging offline?
No, it is cost effective because that installation of this kind of throughout the road, because charging poles will be set like some particular places. But this when it will be throughout the road, we have to lay out this kind of provision. So it will be a little costly. So except that, and we can charging wise, it is good. So we can throughout the journey, we can charge it. Yes, sir.
Okay. Okay. Thanks, Nayak. The next question is by Amrish Kumar. This is also related to wireless charging. Wireless system have very high magnetic flux intensity inside car. Is there any effects on human health?
To some density, it is nothing to affect to the human health and animals also. So because when it will be operate up to 400 kilohertz operation, so up to that field it won't be affect to the humans and animals. So beyond that, so little will be impacted will be there. So that's why the most of the literature and researchers is focusing as per SAE standard. It is 85 kilohertz. So up to 85 kilohertz, nothing will be affected to the human health. Okay, sir.
Okay, thank you, Nayak. There is one question from Ritam Datta. I'm not from electronics background. Could you suggest a book on power electronics which help me get a good idea on power storage EV?
I think Power Electronics by
Any power
Ed
electronics
Mohan or
on power storage?
Power Electronics by H. Rashid. So these two are very good
Vicky,
books.
would you like to answer?
Yes, sir. Power Electronics by Professor Ned Mohan.
Hello.
Hello, sir. Can you hear me, sir?
I could hear.
Yeah.
You're audible.
Some books on power electronics which help me get a good answer.
Yes, sir. Very famous books by Power Electronics by late Professor Ned Mohan, and one more Power Electronics by H. Rashid. So these two are good books for basic level to start.
Yeah, I could not see any questions in my screen. I'm not sure whether it is disconnected, but I could not see anything now. Somebody could see any questions? Okay. Yeah, I could see one questions. One question by it's now loading, and there was some issue in my machine. Sorry. The one question to the to Professor Nayak. There is an anonymous attendee. Name is not displaying. Asking, is wireless charging feasible because during rainy season it may affected by water? Some questions he's asking.
Yeah, nothing will be affected by water or snow or either any dust fall on that system, because it will be completely depend on the magnetic field. So the magnetic field, even if we have the any wall also, it will be field will be linked. So it won't be affected.
Okay. And one question to Mr. Bal Subramanian. I don't know whether he's available to answer. Do we have a standard charging protocol and geometry for the ease of interchangeability in India? Or each OEMs are doing their own? And if so, why not standardize it as it will have more customer benefit? I hope they have a uniform standard, I think. And the another question by Sundaramurthy, can you provide the PPTs used in the presentation? I hope they will provide.
So this this is available live in YouTube.
In YouTube, correct.
Yeah. In the flyer
Even
itself,
have a
the
look at
link
it.
is given. So anytime they can
Yeah.
go to our YouTube channel and see this on the program.
The link, and they can they can read it.
Yeah.
Correct.
The link already they have the link.
Okay. There is one more last question we'll take. There's Kedar Singh Deshmukh. Questions to Mr. Nayak. Do we have a dynamic wireless charging facility anywhere in India so far? Any road track made for it?
In India is not in developed. Maybe in other countries, it will be the Sweden and that SAEW, they are already designing and developing, and in Singapore also, they'll in like MIT, Electricity, they already tested and developed it, but in India is not there. It is under developing, and we have to focus in Indian scenario based on the road and road condition and these all these things.
Okay.
But it is there for static kind of wireless charging. The Mahindra, they are providing, Mahindra automobile industry, they are providing for the static wireless charging provision.
Okay. Okay, that's all the questions asked by the participants. Hopefully, we have addressed most of the questions by the participants, but some questions repeating. So I'm not able to read that, and because of the disconnection, that is also gone. But the attendees can contact the speakers of this program because they have provided their email IDs. Can always contact the coordinators, and you can directly mail them if you have any queries or doubts. So thank you very much to all the participants for your patience and the organizers to organize such a wonderful webinar session on this particular topic. Thank you.
Thank you, sir. On behalf of Institution of Engineers, thanks to the panelists and also to our moderator, Professor and Dean of NITC, for this wonderful session. And of course, to the participants, without whom this could not have been a success. We are looking forward to have similar kind of interesting webinar in future. So with this, I am ending the session, today's session. Thank you.
Thank you, sir.
Thank you.
So now it will.
Yeah, you can leave.
Okay, sir.